All right, so our video for lessons 3 and 5 started to get a little bit long, so we kind of cut it off. This is the second part of that video, so you can just kind of start here um, and finish up with vocab and a couple practice problems. This will be a lot shorter video than the ones we just did. Okay, so we left off with some vocab. We already did sample space, tree diagram, and compound events. Our last vocab word is the fundamental counting principle. And this is a really cool thing. The fundamental counting principle is a way to use multiplication to find the number of possible outcomes in the sample space. So instead of having to make that sample space list or make that tree diagram, the fundamental counting principle is a shortcut. It's kind of like a life hack. And it uses multiplication to quickly find how many outcomes there are in the sample space. So let's jump right into it. Fundamental counting principle. We're going to go back to example 5. That's one we just looked at. We roll a die and then flip a coin. So here's our tree diagram, just a reminder of what that looked like. We had 12 outcomes: 1H, 1T, 2H, 2T, 3H, 3T, 4H, 4T, 5H, 5T, 6H, 6T. That ended up being 12 total outcomes if we had written that out in list form in our sample space. So it would look like this: 1H, 1T, 2H, 2T. You kind of get the point, right? I could write out all 12 of them. I didn't write out any of these 8 here. So instead of having to make a tree diagram or create a big long list, the fundamental counting principle helps us to shortcut right away and figure out how many outcomes there are in the sample space. And here's how we do it. First, we roll a die, then we flip a coin. So there are 2 steps in this compound probability example. Okay, the first step, we roll a die. So how many outcomes are there when we roll a die? There are 6 total outcomes. 1, 2, 3, 4, 5, 6. After that, we flip a coin. How many outcomes are there when we flip a coin? There are 2 outcomes there, heads or tails. And we take those 2 numbers, we multiply them together, and that tells me that there will be 12 outcomes for this compound event, rolling a die and flipping a coin. Really quick, really short. We can check it. There were 12 total outcomes here, and it was much faster to just do that multiplication. This was example 4 that we already did. We flip a coin 3 times, so there are 3 steps. 1, 2, 3. First step was flipping a coin. There are 2 outcomes when we flip a coin, heads or tails. Second step, flipping a coin. There are 2 outcomes when we flip a coin, heads or tails. Third step, you guessed it, flipping a coin. There are 2 outcomes, heads or tails. So we take those 3 steps and we multiply their outcomes together. 2 times 2 is 4, times another 2 is 8. There are 8 outcomes in that sample space. Let's check it. Here was our tree diagram for that. How many outcomes did we have? HHH, that's 1. HHT, that's 2. HTH, that's 3. HTT, that's 4. THH, that's 5. THT, that's 6. TTH, that's 7. TTT, that's 8. So we had 8 outcomes. We could make the tree diagram, make the list, or just do the multiplication. This is really fast. We like this. Example 3 is flipping a coin twice. Well, that looks very similar. Again, we're going backwards and looking at previous examples here. That's why our counting went in reverse. So 2 steps when we flip a coin twice. The first flip had 2 outcomes, heads or tails. The second flip also had 2 outcomes, heads or tails. And that tells me there are 4 total outcomes for that compound probability problem. Really, really nice. Let's see one more of these. Oh, a couple more of these fundamental counting principle problems. Number 6 here, you go to an ice cream shop and decide to make a sundae. There are 5 different flavors of ice cream, 4 different toppings, and you can choose whipped cream or no whipped cream. So that's a choice of 2 there. whipped cream or no whipped cream. So how many different sundaes can you make? This looks like a different type of problem, but it still deals with probability. We could ask a lot of probability questions about this. You have 3 choices. This is how our fundamental counting principle works. 3 choices. Our first choice was 5 different flavors of ice cream. Our second choice was the 4 different toppings. And our third choice was whipped cream or no whipped cream. That's 2 choices there. Okay, so if we want to figure out how many sundaes we can make, we just do a multiplication problem. 5 times 4 is 20, times 2 is 40. There are 40 different sundaes that we can make, assuming that we choose 1 flavor of ice cream, 1 topping, and whipped cream or no whipped cream. Number 7, let's look at this one. You're getting a new lock for your locker. It has a 4-digit code to unlock it. 4 digits. Let's get that set up. How many different codes exist? Well, a 4-digit code, how many digits exist? That's a single digit number. We have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. If you count them up, if we include 0, that's 10 possible digits for my first number in my code. 10 possible digits for the second number of my code. 10 possible digits for the third number, and 10 possible digits for the fourth number. Okay, 0 through 9, 0 through 9, 0 through 9, 0 through 9. If we do this multiplication, 1 times 1 times 1 times 1 is 1. And then we put 4 zeros at the end. 0, 0, 0, 0. That means there are 10,000 possible codes for that combination. That's pretty neat, right? Pretty neat. Think about your security there with 10 different codes. Same problem for number 8, but this time we're saying that there can be no repeating digits. So there are still 10 digits in the code. Still 10 digits in the code, but this time we cannot repeat any. So we can have all 0 through 9. That's 10 digits for the first number. But then whatever number we get here for our first digit cannot be used again. So instead of 10 digits, we only have 9 digits available for our second number. That number cannot be used again, so we have only 8 digits for the third number. That number cannot be used again, and we have only 7 digits for the fourth number. If we want to know how many digits, how many different codes exist, I'll pull up my trusty calculator here. We can do 10 times 9 times 8 times 7, and that is 5,040. 5,040 different digits, different codes exist with those restrictions. So that's how we use the fundamental counting principle. Okay, last thing, compound events. We've been talking about it, but let's see one more thing with compound events. We flip a coin twice. That's my compound event. It's not just one coin flip, it's 2. We're going to find each probability. So we can do this with a method similar to our fundamental counting principle. We have 2 steps because we're doing 2 coin flips, so we can set up our 2 lines. This time we're going to figure what's the probability of the first outcome and what's the probability of the second outcome and multiply them together. So probability of getting heads when we flip a coin is 1/2. Probability of getting heads when we flip a coin is 1/2. We can multiply. 1 times 1 is 1. 2 times 2 is 4. So the probability of getting heads and then heads again is 1/4. Here, same idea. Probability of getting heads is 1/2. Probability of getting tails is 1/2. 1 times 1 is 1. 2 times 2 is 4. This is how we can do probability with a similar method with the fundamental counting principle. Okay, no heads. We'll do this and we'll skip the next one. Probability of no heads. That means tails on the first flip, tails on the second flip. Sometimes we're going to see probabilities written in different ways. You have to just think about, hey, what outcome does that look like? So Tails on the first flip is 1/2. Probability of tails on the second flip is 1/2. 1 times 1 is 1. 2 times 2 is 4. All right, similar situation for that guy. I have another example here. We'll do some of these, not all. Example 9, in a sock drawer, there are 10 white socks, 8 black socks. We reach in and pick a sock. It's not the one we wanted, so we put it back. Then we pick another sock. So what's the probability of getting a white sock first, black sock second? We need to know the total number of socks to do these probabilities. So 10 plus 8 is 18. And then we look at our probabilities. What's the probability of getting a white sock on the first pick? There are 18 socks. Of those 18, 10 are white. Put our sock back in. Now what's the probability of getting a black sock? There are 18 socks. 8 of them are black. So we can do some multiplication here. I'm going to simplify first. I can divide 2 out of 8 and get 4. I can divide 2 out of 18 and get 9. I'm going to do the same thing here. I can divide both of those by 2. 10 divided by 2 is 5. 18 divided by 2 is 9. And now I can multiply straight across. 5 times 4 is 20. 9 times 9 is 81. So the probability of getting a white sock and then a black sock is 20 81sts. Let's look at one more of these. How about white sock, white sock? What's the probability of getting a white sock, putting it back, and then getting another white sock? So there are 18 socks in all. 10 of them are white. Put my sock back. There are 18 socks in all. 10 of them are white. Now I can do some simplifying. 10 divided by 2 is 5. 18 divided by 2 is 9. Same thing here. 10 divided by 2 is 5. 18 divided by 2 is 9. And when I multiply, I get 25 81sts. So that's the probability of picking a white sock and then another white sock. Let's look at this problem and then we are finished. This problem looks exactly the same, except instead of putting the sock back in, we keep it out. Keep it out. So let's do this one. Probability of a white sock first, black sock second. White sock first, black sock second. White sock first is 10 18ths. But this time we take the sock and keep it out. There are no longer 10 white socks in that drawer, there are 9. There are no longer 18 socks in all, there are 17. So when I look at my black sock probability, there are 17 socks in all. Of those 17, 8 are black. Okay? Let's do some simplifying. I can divide by 2. That gets me a 4 and a 9. 10 times 4 is 40. 9 times 17 is 153. So that changed my probability here because I kept the sock out. We're going to look at the setup of this guy here, and then we're going to finish this video. White sock, white sock. Well, whenever we start a new problem, we do reset everything, okay? So we're back. We're back to 10 white socks. We're back to 8 black socks and 18 total socks. So white socks. First, probability of picking a white sock is 10 18ths. Now we keep that white sock out. 9 white socks, 17 total socks. So the probability of picking a white sock on the second pick is 9 17ths. Let's do some simplifying. Divide both of those guys by 9, I get 1 and 2. Multiply straight across, I get 10 34ths. And I can simplify that to get 5 17ths. Okay, so just think about how that affects things for us, this keeping the sock out.